It is not recommended to use the method described to ground electrical receptacles. The National Electrical Code, or NEC, which sets safety standards for electrical installations in the United States, does not allow the use of rebar or bare wires as grounding electrodes. Driving a rebar into the earth may not provide a reliable and permanent path to ground. Soil conditions, moisture levels, and corrosion can affect the conductivity of the connection. Using bare or sheathed wires creates a potential shock hazard if they come into contact with people or other objects. The proper way to ground electrical receptacles in an older home is to install a grounding wire from the receptacle box to a designated grounding electrode, such as a copper-clad steel rod driven into the earth or a water pipe that is in direct contact with the earth. Attempting to ground electrical receptacles using the method described could be dangerous and may not meet code requirements. It is highly recommended to consult with a licensed electrician to discuss safe and effective grounding options. A grounding electrode system is a system of interconnected grounding electrodes designed to provide a low impedance path to earth for fault currents, thereby minimizing the risk of electrical shock and equipment damage. Here's a breakdown of key aspects of grounding electrode systems. Firstly, grounding electrodes are conductive objects that establish a direct connection to the earth. Common types include ground rods, typically copper or copper-clad steel rods driven vertically into the ground, ground plates which are metal plates buried horizontally in the earth, and underground metallic water pipes in direct contact with the earth for at least 10 feet and electrically continuous. Also, concrete encased electrodes, often referred to as UFO-grounds, consist of a minimum of 20 feet of bare copper conductor encased within a concrete foundation or footing, and ground rings, which are bare copper conductors encircling a building or structure buried at a specified depth. Secondly, the NEC, specifically Article 250, outlines the requirements for grounding and bonding. It mandates that all electrical systems be grounded to earth to provide a safe path for fault currents. The grounding electrode system must comply with specific resistance requirements. The NEC requires a grounding electrode resistance of 25 ohms or less. If this resistance cannot be achieved with a single grounding electrode, 2 or more electrodes must be installed, spaced at least 6 feet apart. Thirdly, all grounding electrodes must be bonded together to form a single grounding electrode system. This is typically achieved using bonding jumpers, which are conductors that connect the electrodes. Bonding ensures that all electrodes are at the same electrical potential, minimizing voltage differences and improving the overall effectiveness of the grounding system. The size of the bonding jumpers is determined by the size of the service entrance conductors. Also, the grounding electrode conductor connects the grounding electrode system to the electrical system's neutral point at the service entrance. This conductor carries fault current back to the source, allowing overcurrent protection devices, such as circuit breakers or fuses, to operate and clear the fault. The size of the grounding electrode conductor is based on the size of the service entrance conductors, as specified in NEC Table 250.66. Moreover, proper installation of the grounding electrode system is crucial for its effectiveness. Electrodes must be installed in locations where they are in continuous contact with the earth, below the frost line, to prevent heaving due to freezing and thawing. The connections between electrodes and conductors must be mechanically strong and electrically conductive, using approved connectors and methods. Regular inspection and maintenance of the grounding electrode system are essential to ensure its continued effectiveness. Check for corrosion, loose connections, and physical damage to the electrodes and conductors. Periodic testing of the grounding electrode resistance is recommended to verify compliance with NEC requirements. Low impedance is critical for effective grounding. A low impedance path allows fault current to flow quickly and easily back to the source, facilitating the rapid operation of overcurrent protection devices. High impedance can impede the flow of fault current, increasing the risk of electrical shock and equipment damage. Factors that affect impedance include the type and size of grounding electrodes, the soil resistivity, and the quality of connections. Soil resistivity varies depending on the type of soil, moisture content, temperature, and the presence of salts or other minerals. High soil resistivity increases the resistance of the grounding electrode system, making it more difficult to achieve a low impedance path to Earth. Methods for reducing soil resistivity include driving electrodes deeper into the ground to reach more conductive soil layers, using multiple electrodes spaced apart to increase the area of contact with the earth, treating the soil with ground-enhancing materials such as bentonite clay or conductive concrete. Ground-enhancing materials improve the conductivity of the soil, reducing the overall resistance of the grounding electrode system. The effectiveness of a grounding electrode system can be evaluated by measuring its resistance to earth. This is typically done using a ground resistance tester, which applies a test current to the grounding electrode and measures the resulting voltage drop. The resistance is then calculated using Ohm's law, R equals volts divided by amps. The NEC specifies the methods for testing grounding electrode resistance and provides guidelines for interpreting the results. The NEC also addresses the grounding requirements for specific types of equipment and systems, such as generators, transformers, and sensitive electronic equipment. These requirements may differ from the general grounding requirements and should be carefully followed to ensure safety and proper operation. Grounding is a critical aspect of electrical safety. A properly designed and installed grounding electrode system protects people and equipment from electrical shock and damage by providing a low impedance path for fault currents. Understanding the principles of grounding and the requirements of the NEC is essential for anyone involved in the design, installation, or maintenance of electrical systems. Grounding and bonding are two distinct but complementary concepts in electrical safety. Grounding refers to connecting an electrical system or equipment to the earth, while bonding refers to connecting conductive parts of an electrical system together to create an electrically conductive path. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to operate, while bonding ensures that all conductive parts are at the same electrical potential, minimizing the risk of electrical shock. The NEC requires both grounding and bonding to be implemented in electrical systems to provide comprehensive protection against electrical hazards. Grounding electrode systems play a crucial role in protecting against lightning strikes. When lightning strikes a building or structure, a properly designed grounding electrode system provides a path for the lightning current to flow safely to earth, minimizing damage to the building and protecting occupants from electrical shock. Lightning protection systems typically include air terminals, down conductors, and a grounding electrode system. Air terminals are installed on the roof of the building to intercept lightning strikes. Down conductors carry the lightning current from the air terminals to the grounding electrode system, and the grounding electrode system dissipates the lightning current into the earth. Surge protection devices, or SPDs, are used to protect sensitive electronic equipment from voltage surges caused by lightning strikes, power grid switching, and other electrical disturbances. SPD divert surge current away from the equipment and back to the source or to ground, preventing damage to the equipment. SPD should be installed at the service entrance and at branch circuits feeding sensitive equipment. Understanding the different types of SPD, their ratings, and their installation requirements is essential for effective surge protection. Effective grounding is important for sensitive electronic equipment. Sensitive electronic equipment, such as computers, medical devices, and industrial control systems, are susceptible to damage from voltage surges, electromagnetic interference, and other electrical disturbances. A properly designed grounding system provides a stable and noise-free reference point for the equipment, minimizing the risk of malfunction or damage. Isolated ground receptacles and dedicated grounding conductors are often used to improve the grounding of sensitive electronic equipment. Regular testing and maintenance of grounding systems are essential to ensure their continued effectiveness. Grounding systems should be inspected periodically for corrosion, loose connections, and physical damage. Ground resistance testing should be performed to verify compliance with NEC requirements. Any problems identified during inspection or testing should be corrected promptly to maintain the integrity of the grounding system. Improper grounding can have serious consequences, including electrical shock, equipment damage, and fire. Electrical shock can occur when a person comes into contact with an energized object that is not properly grounded. Equipment damage can occur when voltage surges or fault currents damage sensitive electronic equipment. Fire can occur when fault currents create excessive heat, igniting flammable materials. It is essential to follow all applicable codes and standards when designing, installing, and maintaining grounding systems to prevent these hazards. Grounding requirements vary depending on the type of electrical system and the application. For example, the grounding requirements for a residential electrical system differ from those for an industrial electrical system. The NEC provides specific grounding requirements for different types of systems, including residential, commercial, industrial, and agricultural. It is important to consult the NEC and other applicable codes and standards to determine the appropriate grounding requirements for a particular application. There are many misconceptions about grounding. One common misconception is that grounding protects against electrical shock. While grounding does help to reduce the risk of electrical shock, it does not eliminate it entirely. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to operate, but it does not prevent a person from coming into contact with an energized object. Another misconception is that all grounding systems are created equal. The effectiveness of a grounding system depends on its design, installation, and maintenance. A poorly designed or installed grounding system may not provide adequate protection against electrical hazards. It is important to understand the principles of grounding and the requirements of the NEC to ensure that a grounding system is properly designed and installed. Grounding is a complex and multifaceted topic. This discussion provides a general overview of grounding and its importance in electrical safety. For more detailed information, it is important to consult the NEC and other applicable codes and standards, as well as qualified electrical professionals. Proper grounding plays a critical role in ensuring the safety and reliability of electrical systems. By understanding the principles of grounding and the requirements of the NEC, it is possible to design, install, and maintain grounding systems that provide effective protection against electrical hazards. In addition to the points already discussed, it is important to consider the impact of different grounding configurations on system performance. For example, a solidly grounded system, where the neutral point is directly connected to ground, provides a low impedance path for fault current, facilitating the rapid operation of overcurrent protection devices. However, it can also result in high fault currents, which can cause equipment damage and voltage dips. An impedance-grounded system, where the neutral point is connected to ground through a resistor or reactor, limits the magnitude of fault currents, reducing the risk of equipment damage and voltage dips. However, it can also slow down the operation of overcurrent protection devices. A separately derived system is an electrical system that receives its power from a source that is separate from the main power source, such as a generator or transformer. The NEC requires separately derived systems to be grounded in accordance with specific requirements. These requirements are intended to ensure that the separately derived system is properly grounded and bonded, minimizing the risk of electrical shock and equipment damage. In addition to grounding, bonding is also essential for electrical safety. Bonding refers to connecting conductive parts of an electrical system together to create an electrically conductive path. Bonding ensures that all conductive parts are at the same electrical potential, minimizing the risk of electrical shock. The NEC requires bonding of all metal enclosures, raceways, and equipment to provide a safe path for fault current. Static electricity can build up on non-conductive materials, such as plastic and rubber. Static electricity can discharge suddenly, causing sparks or shocks. In some cases, static electricity can also damage sensitive electronic equipment. Grounding can help to dissipate static electricity, reducing the risk of sparks, shocks, and equipment damage. Grounding is essential for the proper operation of electronic equipment. Electronic equipment is sensitive to voltage surges, electromagnetic interference, and other electrical disturbances. A properly designed grounding system provides a stable and noise-free reference point for the equipment, minimizing the risk of malfunction or damage. Isolated ground receptacles and dedicated grounding conductors are often used to improve the grounding of electronic equipment. Electrical noise can interfere with the operation of electronic equipment. Electrical noise can be caused by a variety of sources, including power line disturbances, electromagnetic interference, and ground loops. A properly designed grounding system can help to reduce electrical noise, improving the performance of electronic equipment. Ground loops can occur when there are multiple ground paths between two pieces of equipment. Ground loops can cause electrical noise and voltage differences, which can interfere with the operation of electronic equipment. A properly designed grounding system can help to prevent ground loops. The NEC contains detailed requirements for grounding and bonding. The NEC is a comprehensive set of standards for electrical safety. It is important to consult the NEC when designing, installing, and maintaining grounding systems. Local codes and regulations may also apply to grounding systems. It is important to check with local authorities to determine the applicable codes and regulations. Qualified electrical professionals can provide expert guidance on grounding systems. Grounding systems are complex and require specialized knowledge and skills. It is important to hire qualified electrical professionals to design, install, and maintain grounding systems. They can ensure that the grounding system is properly designed, installed, and maintained in accordance with all applicable codes and standards. Continuing education is essential for electrical professionals. The electrical industry is constantly evolving. It is important for electrical professionals to stay up to date on the latest codes, standards, and technologies. Continuing education can help electrical professionals to maintain their skills and knowledge. In conclusion, grounding is a critical aspect of electrical safety. A properly designed and installed grounding system protects people and equipment from electrical shock and damage by providing a low impedance path for fault currents. Understanding the principles of grounding and the requirements of the NEC is essential for anyone involved in the design, installation, or maintenance of electrical systems.